Okay, hello everybody. In today's lecture we learn about processes with the goal of understanding how processes work under the hood and how multitasking is realized in modern operating systems. First, we will look at the general concepts behind processes, then how our libc creates processes under the hood, and finally, we will look at how processes can communicate with each other and how this communication is set up. So fundamentally, processes are how operating systems represent different programs and how operating systems allow multitasking by running different programs at the same time. So therefore, the operating system has to manage these different processes and separate their resources, for example, in terms of memory address space through address space virtualization. This means, for example, that each program needs to be able to access the same virtual memory address, but each program can expect different values to be there. This is really useful because it allows the user to listen to music while browsing the web, but it also requires the OS to do all this resource management, like scheduling the processes on the same or on different CPUs, managing the different virtual memory regions, and multiplexing I/O devices between the processes. And this resource sharing and management done by the kernel, by the operating system, is very important because the key idea is that processes are fault tolerant and are not impacted by misbehavior or crashes of other processes. And to do that, operating systems represent, or in particular Unix operating systems like Linux, represent processes with a process ID, which then in the kernel maps to a process descriptor that stores all kinds of process metadata and context. In the case of Linux, this is the struct called task struct, which is quite big. It contains lots of things. PID, of course, register state of the CPU while the process is not scheduled, address space information for the virtual address space, but also scheduling priorities, information on all the open file descriptors, and so on. One of the important fields that we will look at today is the memory management member of the task struct, which contains all the information necessary to construct the virtual address space. So it contains where in the virtual address space what kind of memory is mapped and with which permissions. So how do we create a process? To do that, we use the fork system call, which however doesn't just spawn a new program, but it creates a copy of the calling process. And the relationship between the copy and the original process we call a parent process, which creates a child process. Now Linux is configured to start a initial init process by default, so usually systemd, and then systemd creates child processes, which in turn spawn child processes, and this way your entire system starts up. Aside from processes, there's also threads, which work in a similar way. When you create a thread, you also get a copy of your program, sort of, that runs concurrently. The difference is that forking a process means copying the memory, whereas for threads, the memory is still being shared with the parent. But today we only look at processes. So when fork is called, the first thing that the operating system does is replicate the entire virtual address space to the child process. So we do that with a fork system call, which returns the PID, and we now have two processes which run the same code, but after the syscall returns, each process gets a different return value and can therefore diverge in program flow. So the child gets the return value of 0, and so after the fork call we can check for 0, and then we know that we are in the child. And the parent gets the actual PID of the child in return, so that the branch for the parent process can, for example, use the wait PID system call to wait for completion of the child process. If we look at how our C library implements fork, we will find that typically it doesn't actually use the fork system call, but the clone system call. Clone is basically just more capable. It has more options than fork. And in fact, it is so powerful that it is also the mechanism used to start containers. So this is basically what Docker, for example, uses. And we can investigate which syscalls our C library actually does by using the strace tool. So with strace we can filter for clone syscalls only, and then run bash in this strace environment. Bash is then supposed to fork an ls process, and strace will actually print the syscall that bash does to spawn this process with all the arguments and the return value. And here we see that bash indeed gets the PID of the child ls process back. So the first thing that clone does is copy the address space, right? However, for large applications this will take quite some time, and in fact it is completely unclear if the new process will actually continue using this old address space. So what Linux does to speed up the clone performance is to use copy on write. So the idea is that we have the virtual address space of the parent process and the address space of the child process, and instead of copying all the physical memory pages that are mapped into the parent, instead of copying them and mapping them into the child process, we instead change the memory access permissions to read-only for all pages, which allows us to map them into both processes so that we can avoid the copy. Of course, that means once the child process writes, we have to await a page fault in the kernel. So the kernel will invoke the page fault handler, and only then copy the page that we are the child is just trying to access onto a new page. And then this page, the kernel page fault handler has to map this page into the this new page into the new process, into the child process, and modify the access permissions back to write, because now both processes have their own copy of this page. Yeah, and once this page handler is complete, we can return back to the child process so that it can actually apply the write. And this way we basically lazily copy pages, and if we don't need the pages at all, we will never copy them at all. And this brings us to the next part, because now we have two processes, each with their own address space, but now the new process, in the case of our bash example, wants to run the ls binary. And to do so, we call execve, which actually starts the new binary. And under the hood, again, the syscall used by libcs on Linux is called slightly differently, execve. And yeah, it takes the path name for your executable, the arguments, the command line arguments, and the environment variables you want to pass. And yeah, so in the case, the end-to-end example in our bash case is we have the parent process with the bash binary running, which then forks into a child, which is still running the bash binary. And then the child will look at the return value of fork to determine that it's the child and not the parent. And then the child will run execve with the ls binary, which will wipe the child's address space, load the ls binary into the text, the text and data section, allocate the stack, and then start execution of the ls program. So this is what happens if you directly pass an ELF executable, like a natively executable file in the path name to execve. If it's not an ELF executable, the binary must start with a shebang, like #! Which causes the Linux kernel to use the path as a interpreter. So then this path needs to refer to an ELF binary. And this interpreter will be used to will be loaded into the child and instructed to interpret the path name file. So this is the end-to-end example on how what your libc actually does to create a process. So this brings us to the final chapter of today, which is inter-process communication. So there's two key mechanisms in use in modern operating systems. First are pipes, which expose a similar interface than files. And second are signals, which basically act like interrupts. So let's first look at files. So file descriptors are used in the Linux kernel in the task struct to map an ID to an entry in the file descriptor table. And then this table entry contains all the information that the kernel needs to know where to write to when you write to a file descriptor. And by default, each process has 3 standard file descriptors, which is standard in on file descriptor 0, standard out, and standard error on file descriptor 2. And by default, these are inherited from parents to childs. This can actually be prevented by opening files with the clo-exec flag, because then on calling execve, all previous file descriptors are automatically closed. But this does not apply to these 3 standard file descriptors. And if we want to change how the standard in and so on work, for example, to connect them to pipes, we use the dup sys call. So what this allows us to do is we can allocate we can open a third file descriptor, which will populate the third entry in our file descriptor table. And then we can call dup with this new file descriptor 3 and file descriptor 1 for standard out, for example, which causes the descriptor table entry from file descriptor 3 to be duplicated into the descriptor table entry of standard out of file descriptor 1. And this way we can essentially replace what a file descriptor is pointing to. And yeah, so in this example, the old standard out file descriptor is essentially silently being closed. And so this mechanism becomes important when we use pipes. So to come back to our bash example, we spawn an ls process and then pipe the output of this ls into a second process. So our parent process, the shell, spawns the child process, creates a pipe, and then uses that to connect the ls output through the pipe to the second process input. And to do so, it uses the pipe sys call, which returns two file descriptors, one for the input of the pipe and one for the output. And then the parent has to redirect the standard out of the ls to the input of the pipe. And that's where we use the dup by duplicating the file descriptor table entry of the pipe's input to the file descriptor that used to be the standard out. And so this way we replace the standard out that is behind the file descriptor 1 with the input of the pipe. And then we do the second thing for standard in for file descriptor 0 for standard in of the second process. And this way the Linux kernel now knows that all the output of ls is supposed to go into the pipe, and from that pipe the data is streamed to the standard input of the second child process. And the second mechanism we want to discuss is signals. So as opposed to pipes, which each process has to interact with manually, like you have to read or write by yourself, signals are asynchronous. So they can interrupt the process at any point in time and without the process actively doing much. So examples for this are segmentation faults, which are raised by the operating system or by hardware, or other signals such as that a child process exited, which is called sys-prog. In the end, these signals are just bit masks in the task struct, where each signal refers to one bit, and if the bit is set, then this signal will be injected into the process by interrupting it and calling a handler, a signal handler. Now processes can block some signals if they don't wish to receive them, if they wish to not be interrupted. But some signals like sys-stop or sys-kill can't be blocked because they are directly enforced by the operating system. So yeah, if a process wants to receive a signal or handle them, what it does, it uses the signal syscall to register a signal handler. So basically register a function that the kernel will execute asynchronously, sort of, once a signal is being sent. For some signals like sigterm, for example, there's also default handlers that the Linux kernel applies if the process itself doesn't provide a signal handler. And to give another example of common signals is the sig-child, which is being sent when a child process terminates. And that's exactly what waitPID uses, which is from our code example from fork earlier. waitPID essentially registers a signal handler that waits for sig-child and then just waits until the signal handler is called before continuing execution. Now if bash, for example, wants to send a signal, it uses the kill system call, which you can just specify the process ID and the signal number. And so this is exactly what your terminal does if you press Control, or what your bash does when you press Control C. It will send the sigint signal, so signal number 2, to the currently running child process. Other quite common signals would be sig-kill to terminate a process, which is just enforced by the Linux kernel, sig-child, which we already mentioned, or sig-stop, which is for example commonly triggered when you press Control Z, and this will typically cause your bash to interrupt the running process and put it into the background. so that you can then resume it with the fg command, for example. So these are some examples for signals, but there's many more, and if you want to use them, you will want to look into the other ones to pick the appropriate one for your use case. And then, aside of these reliable signals that we just discussed, there's also real-time signals which behave a little different. But if you're interested, you can investigate these yourself. So with that, thank you for listening, and see you in the Q&A session.